For almost a century, cosmologists have traced the entire history of the universe back to one single, dramatic moment, the Big Bang, roughly 13.8 billion years ago. A new theory, published this month in the journal Physical Review D, suggests that moment might not have been the beginning at all. And if the theory holds up, some black holes drifting through space right now could be older than the universe itself. That's not a typo, and it's not science fiction. It's a real, mathematically worked-out proposal from Professor Enrique Gotz-de-Carga at the University of Portsmouth. And it starts by tackling a problem that's been quietly sitting at the center of cosmology for decades. Here's the problem. Run the equations of general relativity backward, far enough, and the standard Big Bang model hits a wall, a singularity, a point of infinite density where the math simply stops making sense. Physicists generally treat a singularity like this as a warning sign, not an answer. According to Gotz-de-Carga, singularities usually mean our theoretical description has reached its limits, not that we've actually found the true beginning of everything. As he put it, describing the standard picture, space and time emerged from an extremely hot, dense state around 13.8 billion years ago, followed by billions of years of cosmic expansion and galaxy formation. And that picture has been remarkably successful at explaining what astronomers actually observe. The issue isn't that the standard model fails at predicting the universe we see. It's that tracing the timeline back to its absolute starting point runs straight into a wall. Mathematics itself can't get past. So, instead of a universe that starts at an infinitely dense point, this model proposes something different, a bounce. In this picture, our universe didn't spring from nothing. It emerged from an earlier phase of contraction, a colossal cloud of matter collapsing inward under its own gravity. But instead of crushing down into an infinite point, the collapse reaches a very high but finite density, and then reverses, rebounding outward into the expansion we call the Big Bang. What stops the collapse from going all the way to infinity? According to the model, the same basic quantum mechanical principle that already stops other things from collapsing completely. It's the same effect that keeps a white dwarf star from crushing itself out of existence, and the same effect that holds up a neutron star against its own crushing gravity. A kind of quantum pressure that kicks in once matter gets packed close enough together, resisting further compression no matter how much mass is pushing down on it. Gotz-de-Carga's proposal is that the same quantum resistance could operate on a cosmic scale, halting the collapse of the entire universe and triggering a bounce into expansion instead of a singularity. Here's where it gets genuinely strange. If the universe really did contract before it expanded, then whatever existed during that earlier contracting phase didn't necessarily get erased at the moment of the bounce. Some of it, according to the model, could have survived the transition intact. Specifically, black holes. During that pre-bounce collapse, the model predicts that black holes would have formed the same way they always do, through the crushing collapse of extremely dense material. As the contracting universe approached the bounce, some of those black holes could have simply ridden straight through it, carried along into the expanding universe on the other side, essentially unaffected by the very event that created everything else we call the Big Bang. Gotz-de-Carga calls them relic black holes, or cosmic fossils, objects that technically predate the birth of our own universe as we currently understand it. The model actually describes two separate ways this could happen. In the first, called horizon re-entry formation, massive dense regions from the collapsing phase re-enter the observable universe shortly after the bounce and promptly collapse into black holes on their own. In the second, called horizon-shielded formation, black holes that had already fully formed before the bounce survive the transition directly and simply reappear, fully intact, once the universe starts expanding again. Either path produces a wide range of possible relic black hole masses, from relatively small stellar-sized objects all the way up to supermassive ones. And this is where the theory starts solving problems it wasn't originally built to solve. If enough of these relic black holes exist, scattered throughout the universe, their combined gravity could account for some, or potentially even all, of dark matter. The invisible material that makes up roughly 27% of everything in the universe and holds galaxies together, without ever being directly detected by any experiment built to find it. Under this model, dark matter wouldn't need to be some exotic, still undiscovered particle at all. It could simply be old black holes, considerably older than the universe they're currently sitting inside of. There's a second mystery this same idea happens to address, and it comes from an entirely different corner of astronomy. Recent observations from the James Webb Space Telescope have turned up a population of surprisingly massive, surprisingly bright objects in the very young universe, nicknamed little red dots. Many astronomers suspect these are rapidly growing supermassive black holes, but their sheer size, existing so early in cosmic history, has been genuinely difficult to explain using the standard timeline of slow, gradual black hole growth after the Big Bang. If massive black holes already existed the moment the bounce occurred, carried over from before the Big Bang itself, the early universe wouldn't have needed to build them from scratch. It would have inherited a head start. To be clear about where this theory currently stands, it's a serious, mathematically detailed proposal, published in a respected, peer-reviewed physics journal, but it remains a genuinely open, unconfirmed idea, not an accepted replacement for the standard Big Bang model. The paper itself lays out specific, testable predictions, including a distinctive signature these relic black holes should leave behind in the cosmic gravitational wave background. A signal future gravitational wave observatories could, in principle, actually go looking for. That prediction matters because it turns an otherwise untestable idea about what happened before the beginning of time into something concrete enough to actually check. If relic black holes from a pre-bounce collapse really are scattered throughout the universe in the numbers this model requires, their gravitational interactions over cosmic history should have left a specific, calculable fingerprint in the background hum of gravitational waves permeating all of space, distinguishable, in principle, from the gravitational wave signatures produced by more conventional sources like merging stellar mass black holes. Confirming or ruling out this model will depend on exactly that kind of future evidence, not on how elegant the idea sounds on its own. Still, it's worth sitting with the shape of what's being proposed here and letting it actually sink in. For a century, the beginning of everything has meant one specific moment, 13.8 billion years ago, before which the question what came before was treated as close to meaningless, almost a category error rather than a real scientific question. A bouncing universe reframes that question entirely, turning it from a philosophical dead end into something with actual testable consequences. It suggests our Big Bang might be less like a true beginning and more like a reset, one violent, world-scale transition in a much longer story, one that may have left physical evidence of the world before it, quietly drifting through the galaxy today, disguised as the dark matter holding everything else together. Beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.